These are the notes for 3-1, an introduction to functions. I've filled out the vocabulary for you already, but we have 3 vocab words to start: relation, domain, and range. A relation is a mapping of input values with output values. Any ordered pair or any set of data that's mapped with another set is considered a relation. Domain is the set of input values, which can be referred to as the independent variable, and it's usually denoted by the variable x. Range is the set of output values. It's referred to as the dependent variable, and it's typically denoted with the variable y. So we can represent a relation in a variety of ways. We can represent as a mapping diagram, as a graph, as ordered pairs, a table of values, or even an equation. This data set here, this is an example of a relation being expressed as ordered pairs. And all ordered pairs have the x value first and the y value second. So for example, the point -2, -3, x equals -2, and y equals -3. For the next point, when x equals -1, the y value is -2. So for a table of values, all of the x values are going to go in the x column: -2, -1, 0, 1, and 2. And then all of the corresponding y values are going to go in the y column: -3, -2, -1, 0, and 1. Okay, each row represents the ordered pair. For the mapping diagram, this first oval is going to be where all of our x values are, and the second one is going to be for all of our y values. We only need to list each value once. And these are typically in increasing order. Meaning going from the smallest value to the largest value. So for those x values, those go in the first oval, and the y values go in the second. So you shouldn't have any repeating values in your mapping diagram. Just use the number, list the value once, even if it repeats itself in the relation, and try to put them in increasing order. So from here, we use arrows to show the direction, how each x value maps to the corresponding y value. So this input value maps to this output value: -1 to -2, 0 to -1, 1 to 0, and 2 to 1. This is a linear relation, so the mapping diagram looks pretty straightforward, but typically for a relation, I'm just going to fill in random numbers. We would have intersecting maps. So like 3 might map to -4, 2 might also map to -4, and 1 might map to -2. So you can have more than one value mapped to the same value. You can have one value mapped to 2 different values, and those arrows typically would cross a little. Our arrows in this example did not cross because this is an example of a linear function. each x value increases by 1, and correspondingly the y values increase by 1, so the map is straight across. So now for the graph. So we want to plot these points using the horizontal axis for the x values, and this vertical axis is for our y values. So for example, for y it'd be 1, 2, 3, 4. 0 is at the middle there, -1, -2, -3, -4. And then the x-axis is also like a number line, positive to the right, negative to the left. So we're going to plot each ordered pair on this graph to represent the relation. So we'll start with -2, -3. So go to -2 on the x-axis and go down 3. And this ordered pair represents when x equals -2 and y equals -3. -1, -2. 0, -1. So when x equals 0, y equals -1. 1, 0. So go when x equals 1, and it's going to be right on the x-axis. 2, 1. So when x equals 2, y equals 1. Like I said, this is a linear relation, so it's tempting to want to graph a line through those points, but we're just plotting the points because we're just representing the relation as a set of data points on this coordinate plane. So no need to connect and extend. So a specific relation can be considered a function. So all relations are relations, but only some relations are functions. And a function is a relation in which each domain has one and only one range, meaning there's exactly one output for each input. I actually like to refer to so every input has exactly one output. Okay, so each input value can only map to one output value. For a given value of x, it can only map to one value for y. It would be considered not a function if one x value mapped to two different y values. That would be an example of that input having more than one output. So that relation would not be considered a function. But it is okay for the y values to repeat. Certain inputs can map to the same output. Okay, but inputs can't map to two different outputs. So it's okay for y values to repeat, but it is not a function if the x values repeat. So we want to, for each of these displays of the relation, we want to state the domain and the range. So remember, the domain is the set of all inputs. The range is the set of all outputs. And then we want to determine if that relation is a function. So does each input have exactly one output? So the domain for A is the specific x values in that table. So 1, 2, 4, and 7. We use those curly brackets to denote it represents the set of values. Feel free to just use parentheses, or you can just write it. We're not going to be picky here. So the range is the set of all possible y values, or the outputs. So it's just 0. So now we want to determine if this relation is a function. Now, each input value has exactly one output. 1 has 0, 2 has 0, 4 has 0, and 7 has 0. Which means that this is a function because each input has exactly one output. The domain for B is the set of numbers in our input side. I'm going to use D for domain just to keep it short. So it's -1, 2, and -10. The range is the set of all y values, so we're looking at those outputs. And now we want to determine if this relation, if this mapping diagram relation is a function. Now each input has exactly one output. -1 maps to 2, 2 maps to 5, -10 maps to 5. It would not be a function if 2 mapped to both 2 and 5. Okay, that's not the case, so this relation is a function. So again, it's a function because each input value has exactly one output. So now for the graph, we have a scatter plot, and we are relating two things. We're relating how long you study to the score you get on a test. Okay, so the domain is going to be all the minutes that are represented in this graph. The range is going to be those corresponding test grades that you get. So what we want to do is we want to scan this graph from left to right and write all of the x values, all of those minutes that we see. Okay, so the first point we would hit is this. This is 10 minutes, 20 minutes, 30 minutes, 40 minutes, 50 minutes. There's 2 at 60, so we just write that once, and 70. Your domain and range are both also expressed in increasing order, so when you go left to right, those are going to be the values in increasing order. And it's also nice that we won't miss any because you're just writing them as you see them. So for the range, we want to scan from the bottom to the top and write the y values as they come up. So write those test scores. So they earned a 20%, 30%, a 40%. There's 3 students that got a 50%. So again, we just write that value once. And 2 students got a 60%. Okay, so the domain is the set of all possible inputs. In this case, it's all of those times that are represented in this scatter plot. And the range represents all possible outputs. In this case, it's the actual scores on the test that are represented in this graph. So we now want to determine if this relation is a function. So does each input have exactly one output? The answer is no. The input of 60 maps to both 30 and 50. So because that happens, because that x value repeats, we have two students that were at 60 minutes. So it's not a function, because if we were able to write a function, like write an equation, and we substitute the value of x equals 60, it doesn't make sense that we would get out a 30 and a 50. So you just get out one value. So this is not a function. The input value of 60 maps to two different outputs. $30 and $50. All right, so let's continue with this function machine. So picture a vending machine, one of the ones that has the pictures of the soda on the front of the machine. Okay, it's a soda vending machine. Now the images have a Sprite. They have a Sprite, Mountain Dew, Coca-Cola, orange soda, whatever. Now the buttons represent the input, the independent variable. You can press whatever button you want. Now, what comes out of the machine is the output. That's the actual soda cans. So now this is considered a working function machine if I press Sprite and I get out a Sprite. It does not make sense, and it would not be a function if I pressed Sprite and I got out Sprite and Mountain Dew. It doesn't make sense that one button corresponds to two different sodas. That is not a function. Now, it would be okay if I have two buttons that have a Sprite on them. So two inputs map to the same output. That is okay. It is not against the function rules that I can have two different Sprite. It's a really popular soda, two Sprite buttons, and they both come out with Sprite. Nothing wrong with that. That's a function. One button, one input can't map to two different outputs. One soda button can't map to two different types of soda. Unless someone made a mistake. Okay, so try to use that example to help you when you're remembering, but one input value can only map to one output value. Now, there's another way to determine if a relation is a function when you have a graphical representation, and that's by using the vertical line test. So a relation is a function if and only if, when you draw a vertical line, it's a function if it only intersects the graph once. If the vertical line intersects the graph twice, then that is not a function. That fails the test and makes it not a function. So the vertical line test, so draw a bunch of vertical lines. You can actually draw them or you can just visualize. Okay, at no point do these vertical lines that I just drew intersect the graph more than once. So this means that the vertical line test passes. Which means this relation is a function. Okay, graph B, so many intersections. Okay, so this these vertical lines intersected the graph at 2 different places, which makes this relation not a function, and I'll tell you why. So this one failed the vertical line test. So it's not a function. So let's think about the points at where the vertical line intersects the graph. Well, this input value, whatever this value is, let's call it 1. It's saying that x value, when x equals 1, it maps to both 2 and -1. That means that input value, that x value, has more than one output value, which makes it not a function. Let's go back to this study time and the test. If we had used the vertical line test, the vertical line would have intersected that graph at those 2 points because that input value, 60 minutes, mapped to 2 different output values, which is what made it not a function. Okay, we have another scatter plot, so vertical lines. Obviously try to do vertical lines so they intersect the points that are actually on the graph. At no point did it intersect more than once, so this passes the vertical line test. Which means it's a function. And anything can be expressed as a graph. So if you want to take every relation that comes up and either think about it in a graph or actually put it in a graph, you could always use the vertical line test, but you would have to show that if the question was asking you to explain. If you're just looking at a mapping diagram, a table of values, ordered pairs, and you aren't actually displaying the vertical line test either passing or failing, you'd want to use the explanation of each input value has exactly what output. That's the function rule. Okay, so we want to, given these 2 graphs, we want to find the domain and the range of the function. So the domain of A, again, scan from left to right, and determine each of those x values of each of those points. So right here, this is -3, -1, +1, and this x value would be 3. Again, we're looking on the horizontal axis, on the x-axis. What is the x value of each of those points? So then using the same points, we're going to determine the range. So scan from the bottom to the top. The y value of this point is -2. The y value of this next point is 0. This y value is +2. And the last value is +4. If it helps you, write each of the ordered pairs first, and then just write the x values in as the domain and range. That's also fine. So this first point, the ordered pair is -3, -2. This ordered pair is -1, 0. Right, that x value is always first. 1, 2, 3, 4. So the domain was -3, -1, 1, and 3. The range was -2, 0, 2, and 4. Now, for A, that's an example, that's an example of a discrete domain and range. Discrete means it's those specific values and it's not including the values that are in between those specific values. The domain is -3, -1, 1, and 3, and that's it. The range is -2, 0, 2, and 4. That's it. Okay, that's an example of a discrete domain and range. Graph 4b, because we have that line connecting the points, it's an example of a continuous domain and range. Every point that's on that line is considered part of the domain and range. The domain and range is going to be a range of numbers as opposed to specific values. Okay, we will learn more about discrete and continuous in 3-2, so stay tuned. But domain and range. So domain, again, scan from left to right. So the first x value is at -2. And we have everything greater than -2, up until +3. Okay, so x can be anything less than or equal to 3, but it also needs to be greater than or equal to -2. So we can express the domain as a compound inequality. Okay, now it's a compound inequality because it's all the numbers between -2 and 3, including -2 and 3. It's because we have two endpoints of that graph that we can express the domain and actually the range as a compound inequality. So for the range, scan from the bottom to the top. The smallest y value is at -1. The largest y value is at +2. Okay, so this time we're going to use the variable y. So, and it's everything in between too, which is why it's continuous. It could be 3/10, 3/4, 3/5. It doesn't need to be specific values. It's everything between -1 and 2, including -1 and 2. So x needs to be less than or equal, y. Oopsies. Y needs to be less than or equal to 2, but it also needs to be greater than or equal to -1. And we change the variable because we're talking about the range. We're talking about the y values. So the last component of this introduction to functions is talking about independent variables and dependent variables. I've tried to use these terms when we talk about the domain, the inputs, the x values, or the output values, the range, or the y values, because they are directly tied. So the input value is the independent variable, and it can be any value in the domain. So it's typically going to be whatever x is. The output value is the dependent variable because it depends on the value of the independent variable. Okay, so independent can be anything. Doesn't depend on any other set of data. So typically, the independent variable is like number of something. Okay, it's a quantitative variable. Meaning you can count it. 1, 2, 3, 4. in the example of comparing minutes to test scores, the number of minutes is the independent variable and the grade on your test is the dependent variable. This relation is saying that your test performance depends on how long you study. I would argue that is true. You could study for 1 minute, 2 minutes, 0 minutes, an hour, 2 hours. It doesn't depend on anything. However, the grade you get depends on how long you studied. So for the dependent variable, it's some type of qualitative variable. Some type of value, some type of cost, some type of something that has a little meaning. It's not something you can count. Like your test score, like a percent. Like that's not something that you just count. You just count 1, 2, 3, 4, 5. Okay, it represents something. It depends on how long you study. So let's think about the function t equals 19m plus 65. This function, the t variable represents the temperature, and the m is the number of minutes. We're trying to preheat an oven. Okay, so let's first think about independent and dependent. The number of minutes is the independent. That could be anything. It could be 0 minutes, 1 minute, 2 minute, 3 minute. It doesn't matter. Nothing else is affecting that variable. So that's our independent. And again, you can count it, right? Number of minutes. So that makes the dependent variable the temperature. The temperature depends on how long the oven's been on, if you're preheating something. So let's tie it back to domain and range. A recipe calls for an oven temperature of 350 degrees. We want to describe the domain and range in context to this. So 350 is going to be the max temperature. Let's first find out, and obviously 0 minutes is the minimum time. We need to find how long it takes for the oven to reach 350 degrees. Actually, I'm going to use M. And then we also need to find the temperature at 0 minutes. Okay, so we need to find these two missing values so we can describe the domain and range. We can describe the maximum number of minutes, and then we can also describe the minimum temperature. So we want to go back to this function here, t equals 19m plus 65. So let's substitute t equals 350 and find the value of m. Oops, 65. So our first step to solving would be to subtract 65. And divide both sides by 19. So it takes 15 minutes for the oven to reach 350 degrees. Okay, now let's find the minimum temperature. So again, we're going to use T equals 19m plus 65. This time we're going to substitute the value m equals 0. Find the temperature at 0 minutes. Nineteen times 0 is 0, so the temperature at 0 minutes is 65 degrees. That kind of makes sense because it's definitely not going to be 0 degrees. That would be a frozen oven. So 65 is like room temperature. So now let's loop it back to writing the domain and range. So the domain, we said the smallest possible domain, the smallest possible number of minutes could be 0. And then the largest was 15. Okay, so that means that m has to be between 0 and 15, but including 0 and 15. So less than or equal to 15 and greater than or equal to 0. Last but not least, for the range, at 0 minutes, the temperature is 65 degrees. So 65 is the minimum temperature. 350 degrees is the maximum. So we can express this as a compound inequality, right? All values between 65 and 350 and including 65 and 350. So T needs to be less than or equal to 350 and greater than or equal to 65. Okay, let's recap. Okay, relations, you can express them multiple ways. Ordered pairs, table of values, mapping diagram, as a graph. The input values or the x values or the independent variables makes up the domain. The y values, the output values, the dependent variables make up the range. Domain x, range y. Domain inputs, range possible outputs. In order for a relation to be a function, each input value can map to exactly one output value. If one input value maps to two different outputs, that relation is not a function. If two different inputs map to the same output, that can still be a function. The Sprite button on a vending machine should only come out with Sprite soda. Sprite button should not come out with Sprite and Mountain Dew. The button's the input. The soda cans is the output. Now it's okay for two different buttons to both be Sprite, and it's okay that two different buttons result in the same soda. That is still a function. It's okay if y repeats. It's not okay if x repeats. You can also determine if a graphical representation of a relation is a function if it passes the vertical line test. If it fails the vertical line test and intersects the graph at more than one place, it is not a function. That input has more than one output. Domain and range. Domain is the set of all possible x values, all of the inputs. The range is the set of all possible y values of all of your outputs. You can express this as specific values if they're given to you as specific values. That is a discrete domain or range. Or it could be a range of numbers, which we would need to use inequalities to show that domain and range. If the graph were to continue in both directions, then the domain and range could be considered all real numbers, right? X can be anything, all the way from negative infinity to positive infinity. We have two different types of variables. We have independent variables and dependent variables. Independent variables are your quantitative value, typically number of something, and it can be any value in the domain. The range or your output values are considered your dependent variables. The value of that output depends on the input, and it's some type of qualitative variable. So if we have that oven, we have a certain amount of minutes, and the longer we heat the oven, the higher the temperature of the oven is going to be. Number of minutes is your independent variable, the temperature is your dependent variable. That's it for 3-1, Introduction to Functions. If you have any questions, please don't hesitate to ask.